Welcome to area between polar curves. So the idea here, this is just like what we do for area between curves in the rectangular coordinate system. So the idea here is if we have two intersecting curves, that intersecting polar curves that actually intersect in polar, right? So that intersect in polar, as in they agree on the theta, right? So at the same theta, right? Then if we have sort of our one curve inside the other, as long as both are at theta 1 and theta 2, then we can just find the area of the outer one and subtract the inner one, right? So we can find the area corresponding to the outside polar curve and subtract off the area corresponding to the inside polar curve. So we can find the area corresponding to the outside polar curve and subtract off the inside area. So our formula here, we would do that the area is equal to 1/2 was included in our area, and then the definite integral from theta 1 to theta 2. The outside curve would have area, let's do capital R squared d theta for the integral. The inside curve would have a lowercase r squared. And then we do d theta. So here our outside curve is capital R equals capital F of theta. And our inside curve would be lowercase r equals lowercase f of theta. So it's the same idea as we have for finding the area between curves, right? Where we just do outside function minus inside. It's just this time that area requires doing r squared and multiplying by 1/2. So for example, let's find the area between the circle r equals 2 and the circle r equals 4 cosine theta. Here we're doing outside the r equals 2 circle, inside the 4 cosine theta circle. So the first thing we need to know is figure out where these two circles intersect. So let's determine where the circles intersect. So find where the circles intersect. So we set 2. So 2 is equal to r, is also equal to 4 cosine theta. So this means that cosine theta is equal to 1/2. Cosine theta is equal to 1/2 at pi over 3 and 5 pi over 3. But if we go from pi over 3 to 5 pi over 3, that's actually going around the circle twice, right? It only requires us to go around the circle once. We actually want to go, that would be like, if we went from theta pi over 3 to 5 pi over 3, this would be, we start here, we go around the circle, and we go around again. That's too much of the circle. So instead of going from pi over 3 to 5 pi over 3, instead, let's use theta equals negative pi over 3 to pi over 3. So in this case, when theta equals negative pi over 3, we are indeed at the bottom intersection point. And then we'll sweep our way around to the top. So we want to be sweeping, we want to sweep counterclockwise. That's the way that we go around when we go around the unit circle. And so in this case, we would want to go from the bottom point to the top. And negative pi over 3 to pi over 3 does indeed do that for us. So if we do, again, sort of drawing the picture, what we do from negative pi over 3 to pi over 3, this will get both the entire boundary we want for the outside circle, and negative pi over 3 to pi over 3 corresponds perfectly to the region we want for the inside circle as well. So our area then we would do 1/2 times the definite integral from negative pi over 3 to pi over 3 of our outer radius is capital R is 4 cosine theta. Our inner radius is lowercase r equals 2. So we do capital R squared. So we have 4 cosine of theta squared minus lowercase r minus 2 squared, and then d theta. So again, we are looking at 1/2 times the definite integral from negative pi over 3 to pi over 3 of 16 cosine squared theta minus 4 d theta. If you want, we can solve this by hand using our power reduction tricks. So we have 1/2 times the definite integral from negative pi over 3 to pi over 3 of 16 times cosine squared theta is equal to 1/2 times 1 plus cosine of 2 theta. And then we have our minus 4 on the end and d theta. So we are looking at 1/2 times the definite integral from negative pi over 3 to pi over 3 of, we would have 8 times 1 plus cosine 2 theta minus 4. That becomes 8 minus 4, or 4. So we have 1/2 times the definite integral from negative pi over 3 to pi over 3 of 4 plus 8 cosine 2 theta d theta. Of course, we can multiply in that 1/2. We are looking at the definite integral from negative pi over 3 to pi over 3 of 2 plus 4 cosine 2 theta d theta. If we do our integration here, that 2, of course, just goes to 2 theta. 4 cosine 2 theta goes to a 2 sine of 2 theta. We are evaluating from negative pi over 3 to pi over 3. So this becomes 2 pi over 3 plus 2 times sine of 2 pi over 3. Then we are subtracting off negative 2 pi over 3, then plus a 2 sine of negative 2 pi over 3. So this becomes 2 pi over 3 plus 2 times sine of 2 pi over 3 is root 3 over 2. So we have 2 times root 3 over 2. Then we have plus 2 pi over 3. Then we are subtracting off 2 times sine of negative 2 pi over 3 is a negative root 3 over 2. So this becomes 4 pi over 3. Then we have plus root 3 plus 2 root 3. So this is our area between curves formula when our intersection point is a polar intersection point, as in when we're intersecting at the same theta, and it is actually, and the region we're looking at all sort of falls between those angles. In the next video, we will look at a case where they do intersect at specific thetas, but the region that we're looking at between them two doesn't fall on those same intervals of theta.